So good morning, everyone, and thank you for being here at this talk. And as Das said, today my talk will be on machine learning identification of local environments from X-ray absorption spectra. So this is a bit of a change of pace from the previous few talks. So I just want to acknowledge that most of this work was done by my grad student, Chen Zheng, and my previous grad student, Chen Zheng, and my assistant project scientist, Chi Chen. And it is in collaboration with the Materials project. So since I'm the first talk on machine learning, I think I just want to give a very, very brief introduction on what machine learning is, okay? So machine learning has garnered a lot of interest in recent years in many fields, okay? Not just in terms of in science. Hi, someone is actually speaking. I think you need to mute him. Okay. Yeah, so machine learning has garnered a lot of interest in recent years. So you hear a lot of news about things like how they are being used in things like self-driving cars. Whenever you go to Netflix to watch watch something, the recommendations are powered by machine learning. Machine learning actually is nothing new. It has been used for a very, very long time. So every time you get a weather forecast, those are again powered by machine learning algorithms. And of course, the state of the art recently that has garnered the most interest is when machine learning, a deep learning algorithm actually managed to beat the world human Go player in the game of Go. Now, when people talk about machine learning, especially in science, okay, we usually refer to supervised machine learning, okay? What supervised machine learning means is that you basically give the machine algorithm a lot of examples, right? You sort of say when the observation is X, you always get you get Y, okay? And with a lot of examples, what you then hope is that those algorithms would then, without actually giving them explicit instructions, they will actually learn the patterns and infer what the relationship between X and Y is, okay? And with that, then you hope that you can then make accurate predictions going forward. So machine learning, one of the main applications, most high-profile applications of machine learning is in image recognition. Okay, so for example, this was one of the classic machine learning problems where people use this resource known as ImageNet. Okay, so in ImageNet, you basically have lots and lots of images that were collated from the internet, okay, literally millions of images, and each of those images are labeled. Like, for example, this is an airplane, this is a car, automobile, this is a bird, and so on and so forth. Okay, so in the ImageNet competition, people have been trying to basically build better and better models to basically classify these images into various categories. Okay, so all these categories that you see here. All right, so you will notice that in recent years, the performance of machine learning models have improved significantly. Okay, so back in 2010, which was just 10 years ago, every team got at least about 25% of the classifications wrong, which means that they have a accuracy of around 75%. Okay, by the time we are talking about 3 years ago in 2017, most of the teams got less than 5% of the classification wrong. Okay, and in the past 3 years, this has actually further improved. Okay, so in materials characterization, we have an equivalent problem, right? So especially in the X-ray absorption spectra, okay? So when we measure an X-ray absorption spectra, typically what we want to derive from the X-ray absorption spectra that is measured here is really what does it tell us about the coordination environment or oxidation state of the species, right? That is being measured, right? So this is sort of like an image classification problem. So you essentially have some image-like data. So in this case, instead of a two-dimensional image data, you just have a one-dimensional spectra. And what you hope to do is to basically use machine learning to basically interpret what the coordination environment or oxidation state is. Now, typically, before machine learning, the way that people mostly do this is that they compare the measured spectra. Okay, so for example, this is an example from a research work that I was part of, where we basically compare this new electrode material, and we are looking at the X-ray absorption spectra at different states of charge, and we are comparing it to references like the vanadium oxides to try to figure out whether that vanadium is in 2+, 3+, or 2+, 4+, or 5+ oxidation state. Okay, so this is a very typical process in which people try to interpret spectra. Now the question then is, of course, this is a very human-intensive process. Can we do better, right? Can we use a machine to do this for us rather than having to have a human grad student do this in a manual way, right? Now, the problem here, though, is that in order to train a machine learning algorithm, we need lots of data, okay? And unfortunately, experimental data on X-ray absorption spectroscopy is actually hard to come by, okay? So I show you two examples here. So this is, the first example is the ELSIE, which was established in the 1990s, okay? Now, this is just from their website recently, okay? You notice that even today, they only have about close to 300 spectra, and they cover about 43 elements of the periodic table, okay? Now, there's also this resource in Hokkaido University, Japan. This is mainly catalysis data, and they have about 234 spectra, okay? So this quantity of data is nowhere close to the amount that we need to train a reliable machine learning model, right? So our solution to this is to first solve the data problem, right? So the imperfect solution to solving the data problem is, of course, to just rely on high throughput computations, okay? So the code that we use is the FEFF code, which is developed by John Rear in the University of Washington, okay? So using the FEFF code, we first did some benchmarking, okay? So we did, first benchmark various parameters in the calculations to determine what set of parameters would most reliably give us a converged result for a different a set of structures, okay? And we then created an automation workflow, okay, which is shown on the bottom right over here, okay? So the way that it goes is that we start from the Materials project, which is this database of crystals that we have developed since 2012. Okay, it comprises the calculated structures of most of, I would say, known inorganic materials. Okay, we then take each of the structure, we select an absorbing element. So for example, let's say we are interested in vanadium, we will select vanadium as the absorbing element. We then generate the workflow to perform FEFF calculations based on the parameters that we have benchmarked. And then from those calculations, we then store the calculated spectra in a database. Okay. Now, we have published this database already, and we can show that in general, the FEFF code gives a fairly good KH Zanes data. Okay. So, and we have benchmarked all the calculated spectra, for example, for against well-known spectra that we have been able to obtain from the ELSIE and other sources. Okay, so for example, Al2O3, lithium cobalt oxide, lithium nickel oxide, sodium chloride. Okay, and in general, most of the spectra agree reasonably well. Now, so today, if any of you are interested, you can actually access all the X-ray absorption spectra that we have calculated in the Materials project X-ray absorption spectra app. Okay, so the address is right here. Okay, www.materialsproject.org/apps.XAS. Okay, we have calculated about 500,000 KH Zanes for around 40,000 unique materials. Okay, so this is by far, I would say, the largest database of Zane spectra anywhere. Okay, and in the fall of 2020, we are going to add on to this database. Okay, so it's no longer going to be just KH zones, but we are going to add on about 140,000 LH spectra for about 22,000 mostly transition metal systems. Okay, and I would like to show you a real world usage example. So remember, there was this work that I was involved in where we were looking at this disordered rock salt lithium vanadium oxide anode material, and we were trying to basically compare it with various spectra, the reference spectra, to figure out what the oxidation states are. Okay, so using this database, we have actually also been able to compare the experimental XAS spectra with the calculated XAS spectra to validate, to further confirm the changes in oxidation state that we are seeing in this disordered rock salt anode material. Okay, so and all these were done using either existing data that were already present in this XAS app, or it is actually new calculations that were performed using the workflow that we have developed to conduct FEFF calculations in high throughput. All right. Now, so now that we have the data, the question is, how do we build a machine learning model to interpret the X-ray absorption spectra, right? So there are two versions. Okay, so version 1.0, which was the first method that we came up with, is basically matching, right? So we just compare whatever unknown spectra that we have to all the calculated spectra that we have. Okay, so this in other words, this is basically trying to get the machine to mimic human interpretation, right? So we are just comparing to references, and whatever looks most alike, that's basically our answer. Now, in version 2.0, which was just published this year, we actually developed a prediction algorithm. Okay, so here we are trying to learn directly what the relationship between the spectra and the local environment is. Can we just directly ask the machine to look at the spectra and say this is vanadium in 4+ in an octahedral site, right? Rather than having to go through the process of matching. Okay, so this is an approach that has no equivalent in the human-based approach. Okay, so let me quickly go through the first approach, which is the matching approach. Okay, so we have our database of XAS spectra. Okay, basically what the algorithm that we developed was what is known as the Ensemble-Learned spectra identification algorithm. Okay, so it's in other words ELSIE. Okay, now this is based on ensemble learning. Ensemble learning just essentially means that I have a number of learners. Okay, so and each of the learners perform better than random guessing in matching the spectra. Okay, so we take our unknown spectra, we take our database of calculated spectra, and we build learners that combines a certain set of operations on the spectra. Okay, so for example, we shift the peaks, we normalize the spectra or not, we perform some transformations of the features, we normalize the intensity, and we then choose a way of comparing the similarity. Okay, and all that is required for ensemble learning to work is basically that each of these so-called weak learners perform better than random guessing. Okay, so for example, for spectral normalization, we can we use different types of normalization, like we can normalize the sum of the intensities, or based on the sum of intensities. We can normalize based on the square root of the root mean square of the intensities, and so on and so forth. In terms of similarity measures, we chose 4 different similarity measures. Okay, so the standard Pearson correlation, we choose Euclidean similarity, which is just based on Euclidean distance. We choose there's also the cosine similarity and the Ruzicka similarity. Okay, now we built about 168 different weak learners, and from the weak learners, we then chose about 33 that seems to work reasonably well. And basically what this, in ensemble learning, what we do is essentially perform an algorithmic form of democracy. Okay, so we take each of the predictions. Okay, so for example, learner 1 may say that this is vanadium in a tetrahedral site. This learner N may say, learner 1 may say that this looks most like vanadium VO2O5. Learner 2 may say this looks like vanadium in VO2, and so on and so forth. And essentially, at the end, we ask all of them to vote on an outcome, and we combine the vote in a way, and we basically assign a probability based to each spectrum. Okay. Now, we found that this approach actually works surprisingly well. Okay, we for a limited test set of around 19 spectra, we were able to achieve about an 80% accuracy in predicting either the correct structure within the top 5 ranking predictions, and we can also achieve about 80% accuracy in the oxidation state or the coordination environment within the top 5 entries. Okay. So just to show you an example, so this is sodium chloride. Okay, so this clearly works pretty well. So this is the experimental KH Zanes for sodium chloride from the ELSIE, and this is the match the top 4 rank predictions from our ELSIE algorithm, and you see that actually the correct rock salt structure actually appears as the number 1 ranked, and if you look at just compare it with your eyes, it does look fairly similar. Okay, and that's not to say that there are no errors. Okay, so obviously this algorithm, there are certain cases where there are failures. Okay, so for example, sodium oxide on the other hand, the predictions are pretty bad. Okay, so the top rank prediction is actually metallic sodium, while the quite clearly we have an experimental spectrum for sodium oxide. Okay, but sodium oxide does appear as the 3rd rank prediction from the matching algorithm. Okay. Now, I just want to switch to the website to show you a demo. Okay. Let me. All right. So this is the materials project. So if you go to www.materialsproject.org, this is basically the materials project website. You click on the XAS Metro app. You can actually go to choose, for example, the elements, okay, and you choose your absorbing element, and you can ask it to plot the spectra, okay, and what you see here is basically all the computer spectra for different species containing aluminum or oxygen in our database, okay, and you can of course choose different spectra to show and compare, okay. Now, what I really want to show you is this upload and match algorithm. Okay, so if we go to, let me choose the aluminum phosphorus oxygen system. So typically you already know what type of system you are working with. Okay, so I have downloaded the aluminum ALPO4 spectrum from the ELSIE. Okay, you can upload it, okay, and you can, this is based on the ELSIE algorithm, and you can see that you ask it to find matches, and they will try to find what are the top ranking matches for that uploaded spectrum that you have, okay. So this is a tool that is completely open and to the public, okay, so any of you can go in and you upload your experimental spectra to test it out, okay. And I would say that this is we welcome any feedback that you may have on this tool that we have already developed. Okay, so like I said, in the fall, we are going to launch our LH Spectra soon. Okay, and there you will again have the chance to test out with LH. All right, let me now switch back to my slides. Okay. Now, the second approach to predicting spectra is to interpreting the X-ray absorption spectra is using prediction. Okay, so the first thing that we need to do for such a effort is to really rethink about how we featurize the atomic local environment. Okay, so as humans, we tend to have a very I would say somewhat simplistic way of looking at local environments, right? So we always think of a species as being in a 4-fold coordination tetrahedral, or a 6-fold coordination octahedral, and or 8-fold coordination cube, and so on and so forth. And there is sort of no in between to it, right? So even something that may be a very distorted octahedral that looks already close to being a square pyramidal, sometimes we still think of it as an octahedral. Okay, so for example. Now, so what we wanted to do is to relax that constraint a little bit. So rather than classifying things as basically just coordination number 4 or coordination number 6, we wanted a more rigorous and subtle way of describing the local environments. Okay, and the method that we have chosen is to use an order describe each local environment using an order parameter vector. Okay, for each coordination number and motif. Okay, so this is based on the algorithm that was developed by Zimmerman, a colleague of mine in the Materials project, back in 2017. Okay, so for each coordination environment, we have a vector which shows P1 to P12, which tells you what the order parameter of that for each local environment is. Okay, something can be, say, for example, 20% tetrahedral-like and 80% octahedral-like, for instance. Okay, and then you basically have P4 equals to 0.2 and P6 equals to 0.8, right? And the sum of all the order parameters for this coordination number 1 to 12 is basically going to be 1. Okay. Similarly, for the motifs, we can describe an order parameter based on the order parameter for the coordination number as well as the type of motif that we see. Okay. So for example, for 6-fold coordination, there is the octahedron, there's the hexagonal planar and the pentagonal pyramidal local environments, and those are different motifs with the same coordination number. Okay, just to show you how the order parameter number change. So for example, if you take a perfect tetrahedral and you distort the tetrahedral according to the polar and azimuth angle of this tetrahedral, basically you see this fluctuation in the order parameters. Okay. Now, so to directly machine learn the spectral local environment relationship, we basically take our database of all the structures and spectrum. We then take each of the structure and then we classify our coordination number and coordination motifs according to the order parameters. And then we create ranking labels, right? So whether the highest probability is that this is a coordination number 12 or coordination number 1 or coordination number 2. And we do the same for our motifs. And then we give all these spectral coordination number and coordination motif examples to our machine learning algorithm to try to learn the relationship. Okay. So just to show you the distribution of the training data, transition metals are the majority of our data set, okay, followed by the alkaline metals and so on and so forth, okay. Now, the first thing that we did was to first ask the question, what if we knew nothing about that relationship, okay? Let's say we do this, we can do this in a very naive way, right? So if we say that, oh, regardless of what spectra I see, I can always guess that, well, I'm going to use the most common local environment to say that that's the local environment for our species, right? So, and that actually turns out that you do, certain species do have a high prevalence in certain local environments, okay? So for example, if you look at titanium, titanium has 0.89 probability of being in an octahedral site. Okay, so even if you know, even if you have measured nothing, you didn't measure the X-ray absorption spectra, you can find that just by guessing that titanium will be an octahedral site, you'll be right about 90% of the time. Okay, so this serves as the baseline for our machine learning model. Okay, so we basically have to outperform this baseline, otherwise that machine learning model is worth nothing, right? And we can define, using information theoretical principles, we can define what is known as label entropy. So basically how essentially the disordered the local environment is likely to be. So if an environment has many different types of local environments, you basically have very high label entropy, okay? Now, we tried out different machine learning models from k-nearest neighbors to random forest models, convolution neural networks, your standard multi-layer perceptrons and support vector machines. And we basically show that all the models we can achieve at least around, on average, an 80% accuracy in classification accuracy. Okay. Now, we found that, to our surprise, that the random forest model actually works the best. Okay. There is also that there are significant differences in the accuracy of the machine learning model depending on what type of absorbing element we have. Okay. So for alkaline metals, we have the lowest accuracy, but for something like, for example, the transition metals, we have the highest accuracy. Okay. We can show that this is really not limited by data size. Okay. So when we plot the classification accuracy relative to data size for each element, we found that there's really not much of a relationship. While if we plot the classification accuracy relative to the labor entropy, which is how many different types of local environment species tend to have, we see quite clearly that the higher the labor entropy, the lower the classification accuracy. Okay. Nevertheless, we actually managed to get significant improvements in accuracy across the entire set of elements that we tried. Okay, so which encompasses most of the periodic table. Okay, so the highest improvement in accuracy is seen, of course, in the elements with very high labor entropy. For example, our alkaline metals. So, for example, if you just guess that lithium will be in one local environment, you'll be only right about 25% of the time. While if you use the machine learning algorithm, you can get to about a 70% accuracy. Okay. Now, even for the transition metals, the accuracy improvements are quite significant. Okay, we can get an additional 20% accuracy in the prediction of the local environments. Okay. Now, more importantly, okay, other than just being able to predict the local environment from the computed KH-zanes, we also tried to apply this same algorithm which is trained on computer data, to 28 experimental KH-zanes, and we were able to retain 82% accuracy. Okay, so the accuracy is still very high. So if you throw it the KH-zanes, it should be able to give you the right coordination number and coordination motif about 82% of the time. Okay, so we also analyzed the feature importance. Okay, and we show that essentially the pre and main ages are the most important in determining the local environments, okay, especially for the transition metals. And I just want to do a quick demo. Okay, so this is the website in which you can access this tool, okay, which is what we call XAS ML. Okay, so let me again show you. Let me choose an alternative, which is this is my silicon nitride KH-zanes, okay, of silicon in silicon nitride, okay, and from this, the random forest model predicts that there's a probability of 60% that this is coordination number 4, and another 36% probability that this is coordination number 3. Okay. Similarly, this is ARP04, and you see that you can predict. It predicts coordination number 4 with 73% probability. Okay. All right. I'm going to just conclude. Let me go back. And conclusions, with enough data, even complex relationships can be machine learned. If experiments cannot generate enough data, high throughput first principle calculations can be an alternative, a bit imperfect one. And finally, feature importance can also provide insights into the contributions of different spectral regions. Okay. I just want to acknowledge funding from the NSF for this work, and my collaborators in the Materials project, as well as my former PhD student Chen Zheng, who is now actually a data science consultant at McKinsey and earning lots more money than I am, and my assistant project scientist, Dr. Chi Chen. Thank you, and I'm happy to take any questions. Yes. Okay. So how does the deal with spectral alignment? So David, the way that we deal for the matching algorithm, the way that we deal with spectral alignment is that we try to match the onset of the absorption. Okay. So we don't. We found that was the most accurate. We to distinguish between different elements, that's not difficult because the energy scales are very different between different elements. So that one we can do it with almost with 100% accuracy. Okay. So but other than that, for the alignment, we align based on the onset onset of the absorption, and we also perform spectral broadening and shifting to try to match it. Okay. Yeah, we recognize that they might violate some physical principles, but I think, as you know, the computer spectra is not a perfect match to the experiments. Okay. Are we including finite temperature in our spectral estimates? No, we do not. We do not include finite temperature effects, and that you are right. That's probably the reason. Part of the reason why Na2O might be affected, and also maybe the Na2O itself is maybe the calculations for the theory is just insufficient to calculate Na2 the sodium spectra itself. All right, your second question is with respect to coordination number, ability of excited might be modulated by the ability of excited orbitals to describe different coordinations. The higher the local angular momentum of the excited orbital might be more revealing. I would predict that you'll see better performance for the L23 edge. Yes, indeed, David, that's a good point. And we are going to retrain the models using the L23 edges as well. And we might even conceive of a model where we use the L23 edge as one prediction and the K edge as another prediction, and we come up with some weighted prediction, right? So, yeah. Which version of FEFF? The FEFF is version 9. And